Welcome to Video Lessons by CloudDeck. I am super thrilled to have you here for this explainer on mass and balance. You know, when we look up at a massive commercial airliner, we aren't just looking at a marvel of engineering. We're looking at a highly delicate, heavily calculated physics equation balancing midair. Today, we're going to unpack exactly how pilots and dispatchers solve that equation every single day. We're getting highly detailed today. We're going to solve some real-world mass and balance questions together and really master the math that keeps aircraft flying safely. Okay, let's dive right in.
Here's our flight plan for this masterclass. We'll start with the fundamental physics of balance, move into calculating center of gravity, then tackle shifting cargo, payload limits, and finally, the mean aerodynamic chord.
All right, part one, the physics of balance.
So, before we can even think about loading up a multi-million-dollar jet, we really have to wrap our heads around the fundamental forces at play. Think about this for a second. What actually keeps a 100-ton aircraft from just flipping over in the sky? The stakes here are absolutely massive. If the balance point is too far aft or rearward, the aircraft becomes dangerously unstable and it can actually stall. On the flip side, if it's too far forward, it becomes incredibly nose-heavy. The pilots would need massive elevator force just to fly level, which burns a ton of excess fuel and worst-case scenario can cause a nosedive. It really all comes down to the classic seesaw principle. An aircraft in flight is essentially just a giant seesaw balancing right on its center of lift. That fulcrum at the center, that's exactly how we need to think about the center of gravity, or CG. The CG is the exact point through which all the weight of the aircraft acts vertically downwards. If you drop a heavier weight on one side of a seesaw, you either have to put an equal weight on the other side or move a lighter weight further out just to maintain that perfect equilibrium.
To actually calculate this equilibrium in aviation, we use a formula to find what's called a moment. A moment is simply the turning effect around our balance point. The formula is incredibly straightforward. Weight multiplied by arm. The arm is just the distance from a fixed reference point, which we call the datum. Now, pay close attention here, because this is where a lot of people trip up on exams. By convention, any item loaded forward of the datum has a negative arm, and any item aft of the datum has a positive arm. Just remember, weight times arm equals moment.
Moving on to part two, calculating center of gravity.
Now that we have the theory down, let's see how this builds into an actual aircraft calculation. We're going to use this universal four-step process heavily, so lock this in. Step 1, list every single item and its arm. Step 2, multiply those together to find the individual moments. Step 3, sum up all your weights and then sum up all your moments. And finally, step 4, divide your total moment by your total weight. Let's do a highly detailed practice question right now to see how this works.
Imagine we've got a 50-pound structural beam. We set an arbitrary datum point, meaning the center of this beam sits at an arm of 100 inches. Okay, weight 50 times arm 100 gives us a moment of 5,000. Next, let's load a 100-pound weight at an arm of 50 inches. 100 times 50 is, again, 5,000. Finally, we place another 100-pound weight at a 90-inch arm. 100 times 90 is 9,000. Easy enough, right? Now we just sum up the weights. 100 plus 100 plus 50 equals 250 pounds total. Next, we sum the moments. 5,000 plus 9,000 plus 5,000 gives us 19,000 inch-pounds. To find our exact center of gravity, step 4 says we divide that total moment of 19,000 by the total weight of 250, and the answer is exactly 76 inches from the datum. That right there is exactly where our fulcrum has to go.
Let's step it up. Part 3, shifting cargo and loads.
Calculating everything from scratch like we just did is great, but commercial aviation operates in a highly dynamic, fast-paced environment. Picture this. The aircraft is perfectly loaded, the paperwork is signed off, and suddenly an out-of-breath family arrives at the gate requiring a last-minute change, or LMC. Or maybe the ground crew suddenly needs to move cargo from the forward hold to the aft hold just to make room. The clock is ticking. We definitely don't have time to recalculate the entire aircraft from zero.
Instead, pilots and dispatchers use this beautifully elegant shortcut. The formula is simply the shift in the center of gravity equals the mass moved multiplied by the distance moved divided by the total mass of the aircraft. Let's tackle another specific word problem to see this in action. Here's your scenario. We have an aircraft with a total all-up weight of 60,000 kilograms. The current CG is perfectly balanced at 22 meters after the nose datum. However, the loadmaster realizes they need to move 3,000 kilograms of cargo from hold 1, which is located 14 meters after the datum, over to hold 2, which is 29 meters aft.
First question, what is the actual distance moved? Well, 29 meters minus 14 meters is 15 meters. So we are moving a 3,000 kilogram mass exactly 15 meters aft.
Now, let's just plug it straight into our formula. Mass moved is 3,000. Multiply that by our distance of 15 meters, and we get 45,000. Now divide that 45,000 by the total aircraft mass of 60,000 kilograms. The answer? Exactly 0.75 meters. And because we moved the weight backwards, our center of gravity shifts exactly 0.75 meters aft. So our new CG is 22.75 meters. It's incredibly fast, totally precise, and absolutely crucial for real-time operations.
All right, part 4, maximum payload limits.
So we've successfully balanced the load, but we also have to respect the hard structural limits of the airplane itself. The wings and landing gear can only handle so much stress before they literally break. Every single commercial aircraft has 3 critical structural weight limits that we must calculate against. First, there's the max takeoff mass, literally the maximum weight the plane can safely lift off the runway. Second is the max landing mass. You usually can't land as heavy as you take off because the impact forces of hitting the runway are immense. And finally, the max zero fuel mass. This is the maximum allowed weight of the fully loaded aircraft before any usable fuel is added, and it exists specifically to protect the wing roots from bending and snapping.
To figure out how much paying cargo and passenger weight, which we call the traffic load, we can legally carry, we use the lowest of 3 golden rule. You have to calculate the maximum payload for all 3 limits side by side. For takeoff, your allowed payload is just your max takeoff mass minus your dry operating mass, which is basically the empty plane plus the crew, minus your takeoff fuel. For landing, it's a bit different. Because we burn fuel to get to our destination, our allowed takeoff mass is actually the max landing mass plus our trip fuel. So payload equals that combined amount minus the DOM minus takeoff fuel. And for zero fuel mass, payload simply equals the max zero fuel mass minus the DOM. You have to run the math on all 3 of these scenarios. Whichever equation spits out the lowest number, that is your absolute legal maximum payload. You cannot cheat physics.
And hey, we can't just toss that maximum payload anywhere we want in the hold. We also have to account for area load limits. The cargo floor itself has structural limits, usually expressed in kilograms per square meter. Think about it. If you put a massive, incredibly dense piece of machinery right in the dead center of the hold, even if the whole plane is well under its total weight limit, that machine could literally punch a hole straight through the floor. So you always have to calculate the linear and compartment load limits to make sure the weight is spread out safely.
And finally, part 5, mean aerodynamic chord.
Okay, this is the final and honestly most conceptually complex topic today, and it's specifically designed for large, modern swept-wing jets. Look, on a small Cessna, measuring the CG in inches from the nose makes perfect sense. But on a Boeing 747 with those massive swept wings, a simple distance measurement from the nose doesn't actually tell the pilot anything about how the plane is going to handle in the air. So aerodynamic engineers use Mach. They calculate an imaginary rectangular wing that represents the aerodynamic properties of the real swept wing. The front of this imaginary wing is called Lemac, the leading edge, and the back is Tmac, the trailing edge.
Pilots express their center of gravity as a percentage of this Mach, and here is exactly how you can teach yourself to solve any percent Mach question you come across. Step 1. Find out how far back your CG is from the leading edge simply by subtracting LEMAC from your actual CG distance. Step 2. Divide that result by the total length of the Mach, which is just TEMAC minus LEMAC. Step 3. Multiply by 100. So, for example, if your Mach is 100 inches long and your CG is located 20 inches behind LEMAC, well, 20 divided by 100 times 100 means you're sitting at exactly 20% Mach.
This percentage is brilliant because it gives pilots immediate, actionable context. If a pilot sees 13% Mach on the load sheet, they instantly know they're nearing the forward limit and the plane is going to be nose-heavy. But if a dispatcher can perfectly distribute the payload to hit an optimal CG, which is often around 26.6% Mach, the aircraft will require almost no tail-down trim to fly level. Less trim means less aerodynamic drag, and over a 12-hour flight, that literally saves thousands of dollars in jet fuel.
Which leaves us with this final, rather wild reality. You can spend hours on the apron getting everything perfect, calculating your total moments, checking your area limits, and hitting exactly 26.6% Mach. But the second those engines spool up and you take to the sky, the aircraft starts burning thousands of kilograms of fuel. All that mass, it just disappears. So I want to leave you with this thought. During a 10-hour transoceanic flight, as fuel relentlessly drains from the tanks, how will this delicate center of gravity constantly shift beneath the pilot's feet, and what must the aircraft do to survive it? That, my friends, is the true mastery of mass and balance.
Thank you so much for joining this explainer. Keep practicing those formulas, and I'll see you next time.